Space telescopes are expensive things to develop and build and can take years to finish. Just look at the James Webb Space Telescope. That started development in 1996 for a launch in 2007 on a $500 million budget. Now it's looking to launch in 2021 and the budget has reached $10 billion. So when NASA was looking to develop its Wide Field Infrared Survey Telescope, the next big new space telescope after the James Webb, and the National Reconnaissance Office, or the NRO, offered NASA two second-hand but used what would have been spy satellites the same size as Hubble, it was an offer they couldn't refuse. This is the story so far of NASA's new mega Hubble, the Roman Space Telescope. This video is sponsored by Brilliant. The story of the Nancy Grace Roman Space Telescope, more commonly known as the Roman, goes back to 2011 when it was originally known as the W1st, or the Wide Field Infrared Survey Telescope. But in April 2020 its name was changed to the Nancy Grace Roman to commemorate the first female executive at NASA. But why do we need another space telescope? Now we have the Hubble and the soon-to-be-launched James Webb Space Telescope with its much enhanced capabilities. Well, whilst Hubble has revealed more of the distant universe than any other telescope before, the amount of sky it can see in a single image is quite small. If you compare it to the size of a full moon in the night sky, then the patch of sky Hubble would see will be about 100 times smaller. The famous Hubble Legacy Field image is one of the widest high-resolution views of the universe taken so far, and it's made up of nearly 7,500 images taken over 16 years, but it's only about the size of a full moon. The Roman was designed to take images of the universe which would have the same resolution as a Hubble but be 100 times larger. Doing large surveys of the night sky with a Roman will dramatically cut down the amount of time taken. It's been estimated that in the first 5 years of operation, the Roman will collect images covering about 50 times more than the amount of sky than that the Hubble has done in its entire 30-year life. As it's the same resolution, it will be like having 100 Hubbles all working together. Large surveys that would take Hubble literally hundreds of years to complete could be done in just a few years with the Roman. So instead of trying to guess where the best place to look might be, it can just image large amounts of the sky to reveal interesting objects which can be looked at in more detail with the Hubble or the James Webb. The Roman may have 100 times the Hubble's viewing power, but the original Hubble can still do one thing that neither the Roman nor the James Webb can do, and that is look at objects in the ultraviolet spectrum, something that can only be done properly outside the Earth's atmosphere and provides essential information about the formation of galaxies. But there is also the issue that the Hubble is coming to the end of its working life, and even if its orbit is boosted and it can be serviced with one of the new crewed spacecraft, it only has about 20 years left. In its first 2011 incarnation, W1st as it was known then, was going to use a 1.3 metre mirror and have just one instrument, a visible near-infrared imager. However, in August 2011, the National Reconnaissance Office, the agency which looks after reconnaissance satellites used for things like Earth surveillance and classified observations, offered NASA two satellites which had been built for the NRO by the Harris Corporation. These had a 2.4 metre mirror, the same size as the Hubble, and as such could gather 4 times the amount of light compared to the 1.3 metre design and have double the image resolution. As they were originally designed to look down on the Earth from a low Earth orbit, the field of view is much wider than the Hubble's, but that also worked well for the purpose of W1st, to see large areas of sky in a single image. The one stipulation was that these ex-NRO satellites could not be used for Earth surveillance, as that could reveal too much of their classified origins. Some have said that these ex-NRO satellites may be part of the KH-11 Kennan line of spy satellites, first used in 1976 and still highly classified, What we do know is that they were built for the NRO's Future Imagery Architecture program, which was cancelled in 2005. The 2.4 metre mirror in the Roman is the same size as the Hubble and was made from an ultra-low expansion glass but weighs only 1/4 of the weight. NASA has had the mirror reshaped to work better for the mission, and it's covered in a silver coating 200 times thinner than a human hair to better reflect the near-infrared light. During its repolishing, the average size of any bumps and lumps on the surface were reduced to 1.2 nanometers tall. If the mirror was scaled up to the size of the Earth, these lumps and bumps would be just over 6 millimeters high. Because it's so much smoother than required, the scientific benefits will be even better than originally planned. To make the most of the large mirror, the Roman has two instruments, the Wide Field instrument and a Coronagraph. The Wide Field instrument uses a new CCD sensor array with just short of 302 megapixels. To give you a comparison to the Hubble, it has two sensors, one for the visible to ultraviolet spectrum, which is 16.7 megapixels, and the near-infrared sensor, which is 1 megapixel. The new CCDs are also more sensitive to infrared radiation and therefore will be able to see older and more distant objects than Hubble can now. The reason why the Roman and James Webb look in the near-infrared spectrum, which is almost invisible to our eyes and we feel it as heat instead, is because that's where the oldest light from the farthest objects in the universe is now. As the universe has expanded since the Big Bang, the light from the first galaxies, which was in the ultraviolet and visible range when it set off, has been stretched out along with the universe, so much so that it now appears to us as near-infrared. In 2016, Hubble discovered the galaxy GNZ11, the oldest, farthest galaxy in the known universe. And although the light is 13.4 billion years old, when it's properly adjusted for the redshift to compensate for the expansion of the universe in that time, the distance is approximately 32 billion light years away. Both the Roman and the James Webb will be able to see even farther, older objects when they're in service. Survey mapping of larger areas covering millions of galaxies will also help in more accurately determining the rate of expansion of the universe, and hopefully shed more light, to excuse the pun, on what's believed to be the primary driver behind it, dark energy. It could also reveal the earliest sound waves in the universe, the baryon acoustic oscillations from the early universe when it was still a soup of hot plasma, and that are believed to have influenced the distribution of galaxies as the plasma cooled to form the first atoms, then stars, and eventually galaxies. Again, the Roman can do this much quicker than Hubble ever could. In a survey of the Andromeda galaxy, it took the Hubble over 650 hours spread out from 2011 to 2013 to map the area outlined in teal. The Roman could cover the same area in 3 hours or less. The Roman's second instrument is a coronagraph. This is designed to look for Jupiter-sized exoplanets around nearby stars by blocking out the light from the star whilst looking for the reflected light from the planet. A tall order when you think the whole star system might just look like a point of light to us here on Earth. This is only the third coronagraph to be flown into space. The others are on the Hubble and the James Webb, but the Roman one will be 100 to 1,000 times more capable. This is also intended to be a technology demonstrator for future coronagraphs that one day will be able to image Earth-sized rocky planets as a single pixel from stars tens of light years away. The flexible mirrors in the Roman coronagraph, which operate in real time to correct for tiny errors in the telescope's optics, are so precise they can compensate for errors the width of a strand of DNA. These plus high-tech masks bend the light from the star around light-blocking elements. The result is that the blinding starlight is dimmed to a billionth of its original level to reveal any previously hidden planets. But in order for Roman to be able to do this and capture the infrared radiation from the very oldest, farthest objects and make sure that it doesn't get lost in the infrared heat from the Sun and the Earth, it will be much farther away at what's called the L2 point, or the second Lagrange point, about 1.5 million kilometres from Earth, where the gravity for the Sun and Earth cancel out the centrifugal force from its orbit. Here, the Roman will be in a synchronous orbit around the Earth. At this point, far more distant from the Earth than Hubble is, the orbit is more stable and there is less infrared radiation from the Earth. This will help keep the telescope and the sensors as cold as possible, and it means that there will be a 10-fold reduction in the infrared heat contamination compared to the 550-kilometre orbit that Hubble has above the Earth. But what of the second NRO satellite? That hasn't been assigned any plans or funding yet, although there are plenty of suggestions, including studying the Earth's upper atmosphere and auroras to asteroids and other faint solar system objects, or maybe sending it to orbit Mars to produce a high-resolution map which will be 4 times finer than that of the current Mars Reconnaissance Orbiter. If it were to be in orbit around Mars, it would also be better placed to observe the asteroid belt and the outer solar system, but only time and funding will tell where it ends up. The current launch date for the Roman Space Telescope is 2025, and despite the cost overruns in the James Webb program slowing its progress, as of 2019, it was still on target to meet that date. Now, looking up at the stars and wondering what's out there has been done by virtually every person that's ever existed for hundreds of thousands of years. It's been a long journey, but now we're finally getting a grip on some of the biggest mysteries in the universe, with tools to look at and analyse those twinkling lights in the sky that our ancestors couldn't even dream of. But these things need skilled people to create, build and interpret the data they give us. Skills that must be learned, and our sponsors of this video, Brilliant, can help you develop skills in critical and logical thinking. Brilliant is a fun problem-solving website and app, so you're not tied to the desktop and you can help develop those learning skills anywhere. Brilliant breaks down complex problems into small, easily understandable parts before putting them back together to show the overall conclusion. There's no big deal here. If you make a mistake along the way, just check out the explanations to find out more. There are loads of great interactive courses and daily challenges covering everything from the physics of the everyday to logic and scientific thinking and even astronomy, and loads of other things in between. This hands-on active learning approach is great for all of those curious minds of you out there who want to understand the world. If you want to support Curious Droid and get unlimited access to all of Brilliant's in-depth courses and learning, head on over to brilliant.org/Curious Droid to get 20% off of their annual premium subscription. And to close the video, I'd just like to say a big thank you to all of our patrons for their ongoing support.